Hey everyone, and welcome to The Explainer. If you're sitting in a college algebra class right now looking down at a heavy textbook, it's super easy to think math is just done. Like it's a static, finished subject where all the problems have been solved and the answers are already neatly printed in the back of the book, right? Well, today, I want to show you that math is actually this wild, active frontier full of incredible unsolved mysteries. We're going to look at how the exact concepts you are learning right now tie directly into questions that literally the greatest minds in the world still can't answer.
So here's our roadmap for today's explainer. We'll start with defining rationals and irrationals, move into taming infinite series, check out the MRB constant as a case study, weigh the evidence, and wrap up with the unsolved mystery. Let's get right into it.
Section 1. Rationals and irrationals defined. Okay, let's start this foundational review with the numbers we actually use every single day.
Now, in your algebra classes, you're already super familiar with rational numbers. By definition, a rational number is just anything you can write as a nice, clean fraction, a ratio of integers p over q, where q isn't zero. We're talking about your everyday numbers like 1/2, 7/3, or even just -5. And when you look at their decimal expansions, they either stop completely, like 0.25, or they just repeat the same pattern forever, like 0.333. Basically, they represent nice, predictable, orderly algebraic cancellations.
But then, consider the other side of the fence. Irrational numbers. These guys cannot be written as simple fractions. No way. Their decimals just keep going and going forever without ever repeating a pattern. Think of the famous heavy hitters like pi or e or the square root of 2. And here's the thing. This difference isn't just cosmetic. Rational numbers usually come from strong algebraic cancellations, but irrational constants, they usually pop up from deep geometric or analytic complexity. So knowing which category a number falls into actually tells mathematicians a whole lot about its hidden underlying structure.
Section 2. Taming infinite series. Let's see what happens to our foundation when we stop looking at static, single numbers and start adding an infinite amount of them together. Check out this pattern. 1, minus 1, plus 1, minus 1, and it just keeps going forever. Now in algebra, if we add a finite string of these, it's a piece of cake. But what if the string is actually infinite? This is what we call a famously divergent series. Its partial sums just bounce back and forth, right? 1, 0, 1, 0 forever. It never settles down. So, how in the world could we possibly assign a single, meaningful, finite value to an endless tug-of-war like this?
Well, this brings us to this brilliant insider secret in math called Abel-regularization. Here's how they do it step by step. Mathematicians take that unruly divergent series and they introduce a damping factor, let's just call it x, which sits between 0 and 1. When they multiply the terms by powers of x, it miraculously transforms that chaotic sum into a really clean geometric series, specifically 1 over the quantity 1 plus x. Then, for the final magic trick, they take the limit as x approaches 1. And the result? 1/2. Seriously, by using this regularization technique, mathematicians can actually assign a solid value of 1/2 to a series that otherwise just bounces endlessly between 1 and 0. It's basically a way to tame mathematical infinity.
Section 3. The MRB Constant Case Study. With that cool tool in our back pocket, let's introduce the star player of today's explainer. A modern mathematical puzzle born from these exact infinite techniques.
Enter the MRB constant. This was discussed somewhat recently on the Math StackExchange, and it comes from a wildly complicated origin. Imagine that Abel-regularization we just talked about, but totally supercharged. The MRB constant is born from a two-dimensional infinite summation that involves logarithms and alternating terms. It's a beast. And just like our previous example, the ordinary sum completely diverges. It just blows up. But when you apply those Abel-regularization damping factors and take the limit, a highly complex yet totally finite constant pops out of the chaos.
And thanks to some seriously heavy-duty numerical computation, we actually know what this constant looks like. It has a decimal expansion roughly equal to 0.187859, and so on. We can compute it, we can see it, it's a real, tangible value.
But here is the absolute bombshell for you algebra students. Despite knowing exactly how to calculate it, and despite knowing its numerical value to just incredible precision, literally nobody in the entire world knows if this number is rational or irrational. No clue. We simply don't know if this massive, complex, infinite operation secretly collapses into a simple fraction of integers, or if it represents an endless, non-repeating, irrational complexity.
Section 4. Weighing the evidence. Let's put on our detective hats and look at the clues to see which side of the algebraic fence the MRB constant might actually fall on.
First off, there's a really strong circumstantial case that the MRB constant is irrational. I mean, just look at its ingredients. It's built out of logarithms, alternating signs, nested infinite sums, and complex limiting procedures. Historically speaking in math, constants with that kind of analytic complexity are almost always irrational. On top of that, researchers have run super high-precision computations specifically hunting for repeating decimals or simple fraction equivalents, and they've found absolutely nothing. Zero. Plus, analytically, the MRB constant looks a lot like other famous constants like pi, e, and the Riemann zeta function at 3, and all of those are famously irrational.
But hold on a second, because mathematics absolutely loves to surprise us. Check out this brilliant counter-argument. If you take the sum from n equals 1 to infinity of the fraction 1 over n times n plus 1, well, you're adding infinitely many fractions together. It looks incredibly messy, right? But if you actually do the math, all those infinite fractions miraculously cancel each other out, collapsing completely into a beautiful, simple, rational integer of 1.
So the absolutely crucial point is this. We simply cannot rule out that the MRB constant is rational. Could there be these massive, hidden algebraic cancellations buried deep within its two-dimensional Abel-regularized structure? Cancellations that ultimately simplify that 0.187859 into a clean little fraction? Yeah! Theoretically, yes. There is absolutely no mathematical theorem right now that rules this out. Until somebody finds a definitive proof, it remains a total guess.
Section 5. The Unsolved Mystery. All right, let's bring this all home by placing the MRB constant into the bigger picture of mathematical history.
You see, proving that a number is irrational is incredibly difficult. It can literally resist the brightest minds on Earth for centuries. Just look at this timeline. The constant e, which represents exponential growth, wasn't proven irrational until 1737. Pi, the famous ratio of a circle's circumference to its diameter, wasn't proven irrational until 1761. Crazy, right? Heck, even today, we still don't know if pi plus e is irrational. The MRB constant belongs exactly in this thrilling modern frontier. All the computational clues point strongly in one direction, but the ironclad proof we need, still totally elusive.
So what's the big deal? Why do mathematicians care so deeply about whether a number can be written as a simple fraction? Well, the philosophical takeaway here is that asking this one basic question about a complicated number ends up connecting every single branch of math. To solve it, you literally have to bridge infinite series, analytic continuation, numerical analysis, number theory, and mathematical logic. It shows us that there's this profound hidden architecture beneath these seemingly simple questions. Even when the answer is totally unknown, the actual act of trying to solve it deepens our entire understanding of the mathematical universe.
And that brings us to the end of our explainer. The simple fractions, those p over q rationals you are studying right now in your college algebra class, are the exact same tools that are being used to probe the deepest, most unresolved mysteries of mathematics. The subject isn't finished, not even close. It is actively waiting for people just like you to push it forward. So I'll leave you with this thought. When basic questions about numbers can lead to such profound, unsolved problems, what in the world will the next generation of mathematicians uncover? Keep studying, keep questioning, and we'll see you on the next explainer.